to do a huge 180 from what we talked about in the morning. Match filtering was all about knowing what your signal looked like. And so you could dig out your signal, even if the noise is pretty loud compared to the signal. This is kind of the opposite scenario in which we have very little information about what the signal should look like. And so we are trying to see what kind of fits, how we can fit for a signal, or how we can detect a signal when we are in this regime where we don't understand the physics of the process very well. So goals for this lecture are understanding a little bit about stochastic processes with memory, and in particular, studying autoregressive processes, and in particular, AR1 and the continuous autoregressive processes. And at the end, we'll do a little bit. We'll work a little bit on doing model fits and some forecasting with autoregressive processes. Okay. So yeah, like I said, the question we want to ask is how do we analyze some sort of correlated time series of unknown stochasticity? What do I mean by correlated time series? There is some process that's happening, and this process is not random. We have some random noise, but there's on top of the random noise, we also have some process which we don't really understand what that process is or the physics of that, but we do know that it's there. One example of this that a lot of you might be familiar with is something like a Markov process. A Markov process is a stochastic process in which the dynamics of the process depends only on the current position. So this is like a random walk, right? So in other words, if the last n states of the Markov process or n-1 states are x1, x2, x3, x4, x5, and you want to ask what is the probability that the next state is going to be xn, this probability depends only on its current state. It does not matter what x1 to xn minus 2 are. So that's what a Markov process is. Or a Markov changes. And it has memory only of the current state. And so these transition probabilities that tell you what is the probability of going from xn minus 1 to xn entirely define this process. And one example is a random walk or a trunk walk, where the transition probabilities are uniform. And these sorts of processes are used a lot in stochastic methods, especially in Bayesian methods. So for example, if you ever used Markov chain Monte Carlo software, we are doing these Markov process walks underneath the hood. The sampler is doing these Markov process walks all the time. That is how you go from one point in the posterior with an MCMC sampler to another point in the posterior. There are also techniques called hidden Markov models, where the goal is to find like an unmodeled or a complicated signal that's hiding underneath data. And this is something that's especially used.
Can you make sure you're muted on the... Or it might be...
Yeah, I'm muted.
I hear some volume coming out of this.
Okay, thank you.
Okay, so hidden Markov models are something that are used especially with image data, where you have some two-dimensional data, and there is something that's happening in the data, some sort of process that's happening maybe, or some sort of transient, and you don't know what the transient is. You've taken like a large photograph of the sky, maybe. And so hidden Markov models are techniques that help you to actually understand the dynamics of the process without any assumption. So this is these are actually very similar to some of the things that we're going to talk about today. Okay, what we are going to focus in particular are autoregressive processes. An autoregressive process is a random process that retains memory. So this is an n order autoregressive process, and so thus the ith node in the process depends on the previous n nodes plus some omega I. So omega ci's here are deterministic coefficients. Excuse me. They need not be the same at every I, but they are deterministic. There's no randomness involved. They have some functional form. Omega i's are independent random variables. So there is still some randomness that you can put in when modeling an autoregressive process, so that the previous nodes don't entirely determine the next one. And so an autoregressive process of order P, which is usually called an ARP process, will have memory of the current state and the past P minus 1 state, right? So this is an order N process, so it has memory of the current state and the past N minus 1 states. And Pth order autoregressive processes are always continuous and differentiable up to an order of P minus 1. Okay, so far so good. Any questions? Okay. We are going to, yes.
Sorry, if these processes are discrete, then how are they continuous and fractal?
Yes, that's a very good question. I'll get into that in a minute. So we are going to talk about, give me like 5 minutes and we'll get there. Okay. We are talking about, I'm going to spend most of this lecture sort of focusing on the first order autoregressive processes, because they are sort of simpler, and a lot of the mechanics of the Pth order autoregressive process also are present in the first order process. So the first order process sort of only depends on the previous node. It just psi I just depends on psi I and so on. So in some sense, this is very similar to a Markov process. Usually we let omega i's, these random variables, be a Gaussian random variable, in which case the mean, so the first node just has no, it doesn't have any previous node to depend on. So the first node, psi 1, just is just equal to this original random number. It's just an initialization. So in other words, the mean of the first node is 0 if I let omega I be equal to 0, or omega I be a random draw from a Gaussian. And the second node is also 0. You can sort of look at this and reconvince yourself that the second node is also 0. Right, psi 2 is C2 psi 1 plus omega 1 or omega 2. Yeah, sorry, this should be omega 2. And in fact, by induction, all of them are, the means of all of them are 0. But they do have like a more complex covariance matrix. And so if you take psi I plus n and psi n and sort of work through the covariance, you can sort of show that the covariance matrix kind of looks like this. It looks like the variance of the nth term of the nth node multiplied by all of these deterministic coefficients. And the variance of the nth node itself sort of, sorry, it should be I minus 1. So the variance of the ith node itself depends on the variance of the I minus 1th node in this way. And so through these two equations, you can sort of build up the whole covariance matrix effectively. Okay, so you asked if these are discrete, then how do we know how are they continuous, right? because the way to think about this is to imagine these discrete nodes as samples in a continuous in a continuous process that's happening. Let's say you're modeling a light curve. The light curve itself is continuous, but you're modeling, you are going to take data points at some intervals, not necessarily even regular intervals, right? And it is that data that you are fitting, but the process that you are trying to model is the underlying continuous model. So in that sense, and a pth order process will model something that is continuous. And in the continuum limit, there is actually this actually goes back into the theory of stochastic differential equations. So these are differential equations which are not entirely deterministic. So, but they also contain some random numbers that are thrown into the differential equations. And if anyone has done, like, I don't know, advanced grad statistical mechanics, then you might have encountered a similar equation that is used to describe Brownian motion. So in this stochastic differential equation, there are so the underlying process itself is called a continuous autoregressive process, or a CAR1 process. So this is and its discrete samples would represent an AR1 process that we saw in the previous slide. Okay, with me? So this CAR1 process, the continuous autoregressive process, the stochastic differential equation has 3 parameters. There is the time scale of correlation. So this is something that's kind of similar to the correlation time scale that you can get by looking at time domain correlations. There is a variance that tells you how much the process spreads, and there is a mean parameter. And you can show that although you need to sort of solve this differential equation, you can show that if you have a measurement at psi of t prime, then the expectation value for psi of t is given like this. So there is this e power minus delta t psi t plus this extra term. Okay, and the variance of this of psi t given psi t prime is given by this expression. So this is a variance of psi t given psi t prime. Should not be confused by the covariance matrix between psi t and psi t prime. Okay, so what does this actually say? So this is a process that I'm trying to fit. I have a measurement here at t prime. This expectation value tells me what the expectation value of this process should be at any given point in time with t greater than t. So if I want to see what's the expectation value here, or what does the process look like here, then this gives me an expectation value here. This variance tells me what the spread of this is going to be, right? And it sort of makes sense that this spread starts out small at t equals t prime, or it's basically 0 at t equals t prime, and then broadens as time progresses, right? So this is an unmodeled process which has some stochastic nature to it. So the only restriction we are imposing on this, because this is a CAR1 process, is that it has to be continuous. We're not even saying that it's differential. So the only restriction that we have is that close to t prime, psi of t should be close to psi of t prime. As you get further away, the difference between them will increase by quite a bit, or can increase by quite a bit. So we can now use these two expressions, the mean and the variance, to construct a probability distribution for psi of t given psi of t prime. So let's define psi hat of t which is the expectation value of t given t prime. This is the same expression that we saw in the previous slide, minus b times tau. Okay, so b times tau is just coming from here. So that is equal to e to the minus delta t over tau psi of t hat or t prime minus b of tau. And similarly, let's call this omega t. That's just the variance. I'm just using the notation, using some notation here to make it look. Make it look nicer. So we can put these two together, and what we know is that this term psi hat and where did psi star? Yeah, okay. Psi hat then should psi hat conditioned upon psi t prime measurement should look something like this. It's a Gaussian where with a mean of psi hat and a variance given by this, where psi star is given by psi of t minus beta t or beta, not beta. So just to reiterate, this gives the mean of the process at the new point, and this is the mean of this psi hat is not the mean of psi of t, but it's the mean of psi of t minus this beta b at b times tau. And so that is why we define this new parameter here called psi star, and this way we can get directly a likelihood for psi of t given psi of t prime. And this is, so what we are basically showing is now if you go back and sort of compare this with the discrete autoregressive process that you were looking at before, you can kind of see that this directly depends on, or this process sort of depends on the previous node, where e power minus delta t over t is the continuous variable, and this term here is providing the randomness. The variance is just providing the randomness for the continuous autoregressive process. So what are some applications for this? We can do unmodeled Bayesian fitting, and the second application that we look at, although this is turning out to be a little bit more finicky forecasting with AR1 processes than I had expected. I had never tried forecasting with AR processes before, although I hear this is very popular in stock market forecasting. So if anyone is interested in going to finance, this is sort of something. These are sort of the techniques that would be useful in that domain. And we can also do like maximum likelihood versions of both of these. But when you do a Bayesian forecasting, you sort of are able to marginalize over your uncertainties better. Okay, I know that many of you are familiar with Bayesian inference, but I'm gonna take a few minutes to do a very quick intro so that I can make sure that everyone is on the same page with this. Does anyone have any questions so far before we get there? Yes.
So in the beginning, you showed like the XCMC and you show also the comparison like how better it is than the if you implement the same problem.
Yeah.
And we can implement Autoregressive on a specific kind of problem.
I mean that's a very good idea for a hackathon. Take a light curve or something and try to see if you can do that. Yeah, so there's not going to be a lot of astronomy in this session. I'm mostly going to show some of the data analysis technique. Yes, question. Yeah, b times tau. we are defining psi hat that way because sorry. Okay, so because we are trying to compare this with an autoregressive process. So what does an AR1 process look like? AR1 psi of t is given by some continuous deterministic variable times psi of t prime plus omega, right? That's what the discrete process would look like. Or the continuous autoregressive process, what we found is t over tau psi t prime plus t times tau. I think I'm doing this. And by the way, I think I forgot to define it, but that t is simply t minus t prime. So and the way so what we want to do is this is the estimator. This is just the mean term. So the mean term here, if I compare this with this, psi of t should be c times psi of t prime. Right? Clearly, this does not look like that. E of the mean of psi t doesn't look like the mean of psi t prime. So that's the thing that we're trying to change there. So if you write this instead as e times psi of t, I'm going to skip the condition part of it's implied minus b tau. Then you can write this as right. So now this does in fact look like this, because this is already data. It's sort of conditioned. This is the value of the process. There is you're not trying to predict what's happening at t anymore. You're trying to only predict what's happening at t prime. So this is essentially the same as saying that. So if you compare these two now, psi of t minus bt is in fact an autoregressive process, right? We can, because b and t are both deterministic, we can actually write this that way. Does that make sense? Yes.
So is it correct to think of this as like a Gaussian process with very small covariance matrix, like relating neighbors?
Wait, why is the covariance matrix small?
Because phi of t only depends on phi of.
In that sense, yes, an autoregressive process, an AR1 process with like a Gaussian omega is in fact equivalent to a Gaussian process. Yes. Okay. Any other questions? We can chat about that maybe after this. Yeah, about this. Okay. Let's do a brief introduction to Bayesian inference. And I know many of you are familiar with this, so please bear with me. So the central sort of thing that you care about when you're doing Bayesian inference is Bayes' theorem, which relates p of some parameters theta given data with your likelihood, and your prior. So here in this expression, this is just a statement on conditional probabilities. So there is nothing like too esoteric about Bayes' theorem. M here is just some model or hypothesis that you have. So for example, maybe your model is that the data contains a binary black hole merger. Inspired, not inspired. Pi here is called the prior distribution. So this is your prior belief, your existing belief on what the model, on what the parameters of this model should be, of this signal or of this data should be. And theta are the model parameters in question. For example, the masses, the spins, etc. If the model is that it's a binary black hole inspired. PD given theta is called the likelihood function. So this tells you if I have a signal that looks like this, what is the probability of getting getting data that looks like this? So if you think about it, the likelihood is just the distribution of the noise statistics of the model, because we are sort of fixing the signal parameters. And the thing that you want, the thing that you care about, is the posterior probability density, which is the PDF of the parameters of this model, given that we've seen this data. And V here is called the Bayesian evidence, and it's usually used as a measure of model goodness or goodness of this. So how do we do? So as I said, we want to calculate the posterior distribution P theta given D. How do we actually do this in practice? We can create a model in grid space and estimate the likelihood, for example. But that can become very hard very quickly. So let's say you want to create a grid so that there are 100 grid points in every dimension. You can do that for a two-dimensional model, right? So that's 10 to the 4, 10,000 points, which is not too much. But let's say you have a 6-dimensional model. That would give you 10 to the 12 parameters, right? That's basically impossible. You're never going to calculate a grid of 10 to the 12 parameters. A binary neutron star merger inference can have 16 parameters. And there are parameters, there are problems where there are even more higher dimensional spaces. So this quickly becomes untenable. The other way to do this is to use a kind of Monte Carlo sampling. And there are two sort of main samplers of this sort that are used, which are called nested samplers and Markov-Chain Monte Carlo samplers. The way this works is, like, the principle at least is quite simple. And this figure is an example of how MCMC or Monte Carlo samplers work. So let's say you have this complicated shape, and I want to find the area of that shape. One way to do that is to actually, maybe if you know the analytical form of the shape, you can do a contour integral, or maybe you can put it on a grid paper and sort of measure what the area is that way. A third way to do that is to throw a bunch of points randomly in a space that we know the area. So I know the area of the square, it's 4 units. And so I put this thing in the square, and I randomly chuck, I don't remember how many I put here. I think like 1,000 points or something. And the area of this figure should approximately be equal to the number of points that land inside the figure, or the ratio of the number of points inside the figure versus to the total number of points. So here I put in 1,000 points, and I think something like 460 of these points landed inside the figure. So the area of this figure is approximately 0.46 times 4 being the area of the square. And that's and it's basically higher analogs of this that higher dimensional analogs of this that Markov-Chain, that Monte Carlo samplers actually are trying to do. There are newer techniques inspired by machine learning algorithms nowadays called normalizing flows or flows in general, where the idea is you have your posterior distribution that you're trying to find. You find a Jacobian so that you can transform the posterior distribution into a distribution which is very easy to model. Let's say like a Gaussian. So if you have a 10-dimensional distribution that you're trying to model, you convert that into a 10-dimensional Gaussian. And all you need to do is to find the Jacobian that transforms this shape in the 10-dimensional space into a 10-dimensional normal distribution. And then you know what the PDF of the normal distribution is, even in the 10-dimensional case, then you can undo the Jacobian and you get the PDF of the 10-dimensional complicated shape. So these are kind of new and very exciting methods. There are a lot of applications. We're not going to go into that. Okay, so the first application for this is unmodeled fitting, and I am going to walk you through a notebook on. Okay, any questions so far? Okay, so as I said, there's going to be very little astronomy today. So sorry about that if that's disappointing. But it's mainly going to be about how to use autoregressive processes for very simple cases. Okay. So let's first make some simulated data that we can use to fit an autoregressive process. And I wanted to make something that has sort of like a power law shape with some complicated feature. With some complicated structure, so it sort of looks like a light curve, right? And so this is sort of the shape that I have. Can you actually see the code in the notebook? Is that big enough font size at the back? Okay. How about now? Okay. Give me 1 second. Okay, so this is some simulated data that I made with which looks like a power law with some structure. So the blue curve here is the actual data as a function of time, and this orange trace here, it's just kind of faint. But this notebook, I have a link to this collab notebook on the README in case anyone wants to just follow from their own computer. Is the underlying simulated signal that I have, and the noise itself is just standard. It's just uncorrelated time domain Gaussian noise. Okay, so now we are going to do unmodeled fitting and try to recover this this curve. We are going to use a sampler called Dynasty. Dynasty is a nested sampler. How many of you are familiar with nested samplers? Okay, so I think an introduction would be useful. Nested samplers work by the goal of a nested sampler is to try to capture or try to measure this evidence term. And in the process of calculating the evidence, you get the posterior distribution as a byproduct. And the way nested samplers work is they generate proposals from a unit hypercube. So from an n-dimensional unit hypercube. So what I mean is, for each parameter for each independent parameter that you're trying to fit, theta I is drawn from u of 0 to 1. And there are n of these parameters. That's why it's an n-dimensional unit hypercube. So we need to provide a nested sampler 2 functions or 2 methods for it to work. You need to provide it a prior transformation function that transforms draws from this unit hypercube into draws from the prior function or the prior distribution that you are putting in. And next you need to provide a likelihood function that will then allow you to calculate the likelihood of those points. So here this AR1 function is the prior function, and I have this log likelihood function that is calculating the likelihood. So the likelihood is based on this likelihood that we saw just now, where P of psi of t conditioned upon psi of t prime, this older measurement, and these other ensemble parameters, tau, sigma, and b, is just given by this Gaussian, which looks like this, right? Where psi hat is given by e to the minus delta t over t, psi of t prime minus beta. And psi star is just psi of t minus beta. And this is the variance of it. So you can sort of group all of these together. So now you can say, okay, what is psi of t prime given a previous measurement, and so on and so on. So you can construct this likelihood function, which is what is p of, which is the probability of psi of t1, psi of t2, psi of, and so on up to psi of tn, given your ensemble parameters. And this is just this product of all of the Gaussians for each of these psi of t's that are multiplied together. So this gives you the probability of the autoregressive process itself. You still need to put in a likelihood for the data because the data is noisy. So this is P of D, P of data, given all of your size. And so this is just this is again just a Gaussian because the data is Gaussian. But here now the variance is the variance of the noise rather than the variance of the process. Okay, and di is the data at the ith time step. So we have this continuous process, but we can only ever measure discrete points on this process, right? So that's sort of what we're doing. Any questions so far? This seems straightforward. Okay. So now I'm writing this, I'm putting all of these together. The number of parameters I have, each of these psi t's is an independent parameter. So I have number of same number of parameters as I have number of data points because this is not assuming any model at all. I'm modeling each data point independently. Plus I have these 3 extra parameters that are controlling the sort of the ensemble behavior of the process itself. And this is a prior, so I have this transformation function that is transforming each of these parameters from their unit hypercube draws into actual draws from this prior. In particular, for all of these psi i's, I'm implementing a prior so that psi of I is between -6 to 6. Why this number? It's just number effect. And this is the likelihood function. So I'm defining my psi stars, psi hats, and I'm putting everything together to calculate this log probability for the autoregressive process. So that is the logarithm of this. And in addition, I also have a log likelihood, which is the logarithm of this. And usually, when you are working with when you are trying to take products of many terms, as you are here, to calculate the likelihood function, it is usually better to work with a log likelihood function so that you don't get overflow errors. So I calculate these two logarithmic log probabilities, and then I sum them up so that I get the total log probability. Now let's set up the nested sampler. I set up the number of live points, which is the number of points that it's exploring in the parameter space at any given time, and a termination condition. Now I'm plotting the global parameters for the ensemble parameters. So this is the distribution of B, and it's pretty peaked at 0. This is the distribution of tau, and I get a distribution for sigma. So these are not entirely unconstrained, which is showing that the data points. So the fact that these are not unconstrained, that there is some. So for example, sigma is less than 0.8, right? This is showing that the process that I'm trying to model is not entirely random, but there is some structure, and we are indeed capturing that structure. And you can use the draws that you have taken to actually try to reproduce the process itself. So each draw here, each squiggly line here is a draw from this autoregressive process. And on top of that, I've plotted the simulated signal as well. So it sort of recaptures the dynamics of the signal without getting too much affected by the noise, right? And yeah, so that's sort of this first notebook. Yes.
Could you please clarify what are the three parameters, like in relation to the, I guess one is B, the other is tau.
Yeah, one is B, the other is tau. The other one is sigma, which is coming from the variance. So when we were talking about when we set up the likelihood, B and tau show up in the mean, but there is a sigma term which is present in the variance. And this, if you go back to the actual differential equation, this epsilon of t is actually the error term here. So this is in the stochastic differential equation. This is the term which controls how randomly the solution for the stochastic differential equation behaves. And so sigma is a scale variable that controls that. Any other questions? Yes. Yeah, so this is a maximally unmodeled process, which is why we are modeling each node as an independent parameter. There are other ways to do unmodeled fits where you can, for example, people work to do spline fitting, where they use splines are just segments of a polynomial. And they use that to do unmodeled fits, where you can get away with, where you can do the smaller number of fits. An autoregressive process is usually used for something where you have very little knowledge of the underlying mechanics of the process. So you want it to be maximally unmodeled, and you want to give it like as much freedom as you can. So the only condition we are sort of imposing on the autoregressive on the AR1 process is that it is continuous. For the underlying continuous process, it's modeling. You can of course like go like you can make it more more restrictive. And so if you go to an AR2 process or an AR3 process, that does give you more restriction, because now we are saying, oh, the underlying process doesn't just have to be continuous, but also differentiable, then second order differentiable, and so this is like sort of the most unmodeled and the simplest thing.
I guess you understand.
Yes, yes, you only determine the distribution of the second data point, right? So these are all deterministic. But there is this omega I, which is actually a random variable. So it is introducing some randomness into the expression, or into the next node. Any other questions so far? Okay, should we take a quick break? Are we scheduled for a break now? Yes.
We're gonna go straight into the problem session, but we can take a 5-minute break.
Ah, okay. Okay.
Like after lunch, we'll do a 5-minute break.
Okay, yeah. Let's maybe meet back at 2:30 then.